I just graduated my PhD, so I'm just a postdoc so far. But thank you. This is joint work with Emiliano Dalanes and David Bortz, both professors at University of Colorado Boulder. And it's an extension of the W-SINDI algorithm that was the basis of my PhD. And it's the online version of this algorithm for identifying, in this case, partial differential equations from data in an online fashion where data is sort of streaming in. So an example of that is on this title slide. We're trying to identify a nonlinear wave equation. And in this case, the wave speed is varying over time. And the way that it's varying is on the right. It's sort of taking these abrupt dips and jumps periodically over time. And what we'd like to be able to do is identify the correct model and track this wave speed as it goes through those changes, which we'll show as the algorithm does rather well. So first we'll review W-SINDI in the batch case, and then talk about this online extension and some conclusions from there. So the problem that we're trying to solve is the following data-driven model selection problem, where you assume that you are given a data set called U, which is the sum of some true solution plus noise, and you assume that the true solution solves an equation like equation 1, which says that the time derivative of U evolves according to the operator A. So the problem is to infer the operator A directly from the data set U that you're given. This is slightly different from the operator inference problems that other speakers have considered, where we have an input pair and an input-output pair, and a series of those that we can identify an operator from. In this case, we just have one data set, and we propose a model like equation 1 and try to identify that given the one data set. Some areas where this is useful are the following four, depending on how much is known about the operator A. If almost nothing is known, then we might be in the realm of scientific discovery, and a lot of problems in biology fall into this category, where it might be infeasible to derive a model from first principles. If we know something about the model, then we might be in the closure modeling category, where we're trying to use the data-driven modeling approach to close the model. We might actually know the model. We can write it down analytically, but we might want to use data-driven modeling to arrive at a faster version of A. So that's sort of reduced order modeling. And then, given a data-driven model, we could attempt any of the things that we might attempt on a model off the shelf, sort of analysis, control, prediction, experimental design, etc. So this is the problem that we're looking to solve. A popular way of solving this is the SINDI algorithm, sparse identification of nonlinear dynamics. It was proposed a few years ago and has only grown in popularity. And this is due primarily to the generality of the approach and the hopes of this being a very computationally efficient way of doing this kind of problem. So to start off, we take the operator A and we represent it as a linear combination of terms from some library theta. And we assume that theta is large enough to encapsulate a whole host of models, and we could include nonlinear functions of the data, derivatives of the data, nonlinear functions of derivatives of the data, etc., into this library. And from there, it's pretty much these two steps. So you evaluate equation 2 at the data set that you're given. So approximate the time derivative, approximate all the terms in the library using the data, and then we solve a sparse regression problem for the weights that govern the model. So there are at least two issues with this approach that motivated us to consider a weak formulation. The first is that approximating derivatives from data is known to be unstable, and there are some ways to get around this. But if we use, let's say, a finite difference approximation, and we have noise on our data set, then we'll find that the error that we accrue is inversely proportional to the mesh width of the data, so that if we were to refine our mesh and hopefully get a more resolved solution, our approximation to the derivative might actually blow up. So this doesn't happen with every method, but with a lot of methods for approximating derivatives from data, this is the case. The other issue is that the solution U that is the quote unquote true solution might not actually solve the model that we're looking for in a classical sense. It might solve it in a weak sense. It might be a non-smooth function. And so we have to confront both of these issues when we're dealing with problems in biology, for instance. And an example of that is this data set here. So hopefully you can all still see the slides. But this is a wound healing experiment conducted in Chudong Liu's lab of biochemistry at CU, where cells are grown in a plate and then half of them are scraped away. And the natural tendency for these cells is to just migrate into this open space. And so this is a kind of problem that we'd like to use data-driven modeling to arrive at an appropriate model for. And as you can see, it's both very noisy and has a sharp front where the cells are, so that this won't be a smooth solution to any PDE that we're looking to describe this behavior with. So this kind of motivated the weak approach that I'll describe. So to arrive at a weak formulation for this Cindy type algorithm, what we have to do first is reinterpret the model or reinterpret this library theta as having terms that are taking a specific form. So they're given in this box on the top right here, where a linear differential operator, or it could be a linear integral operator, but it's a linear operator acting on a nonlinear function of the data. And if we're given a library full of these kinds of terms, then we can integrate by parts, and that turns out to be an important step. So this is the library type of library that we're considering. We then take this equation and multiply by a smooth enough test function psi that's compactly supported within the domain of the data set that we're given. And we integrate over space and time to get equation 4, where we now have integrals on both sides of the equation, so inner products with the test function, and we've moved all of the differential operators onto this test function using the compact support and the smoothness that we're assuming. So from here, we can select a family of test functions, and this will give us a linear system that we can then solve in the sparse regression sense as we did before. Only now each row of the linear system corresponds to a different test function, and instead of approximating derivatives of the data, we have to approximate integrals of the data. So we've sort of traded this for that, but we'll see that this is a more fruitful way to proceed with in particular noisy data. So the big question at this point is what test functions can we choose so that this recovery scheme is efficient? You can think of integrating a large family of test functions as being a computationally inefficient way of doing this, but we'll actually see it's the opposite. What test functions can we use that will ensure this is accurate if there isn't a whole lot of corruption on the data? And then how can we ensure that this is actually robust enough to handle the kind of noise that we see in experiments? So these were the questions that we've been most interested in answering. And our proposed answers for this is the next couple slides. So for the efficiency piece, instead of looking at these inner products as against a single test function psi k, the first thing we do is say that each psi k is a translation of some reference test function psi. So when it's written like this, then we just have to find one test function psi, and then think of moving that over the space-time domain that we're given. If we do that, then we can interpret these inner products as a convolution. So this gives us the quote-unquote convolutional weak form that's in equation 5. And we're just evaluating that convolution at these different query points within the domain. If we further consider that this test function psi is separable over the space-time coordinates that we're given, so it's just a tensor product of one-dimensional test functions over x and t, then we can approximate equation 5 from the data using just a series of one-dimensional FFTs. So in this case, we get a very efficient scheme because all of the terms in the linear system that we're approximating have a sort of log n factor instead of having to approximate each of these inner products separately. As far as what single reference test function to pick, this goes back to the work that we did in the context of ordinary differential equations, where we were trying to identify ODEs from data. And what we found through some experimentation was that a certain class of test functions were able to afford us arbitrarily high accuracy recovery of the model that we were looking for in the zero noise case, controllable by some parameters in that test function. So the test function class we're talking about is in the box on the top right. It's a piecewise polynomial, sort of Gaussian shaped but compactly supported function that has two parameters. It's got a shape parameter a that determines the support that this function is over, and a degree p which determines the smoothness of the test function. So that p this phi test function has p minus 1 derivatives. So if we use this test function and we use the trapezoidal rule to approximate integrals, what we see is this trend on the top left here, where if we increase this value of p, we can achieve arbitrarily high accuracy recovery of the weights that we're looking for. And this is, again, in the zero noise case. But if we get, say, p equals 7, then we're looking at 10 to the minus 10 error in the weights. And the only reason it's capping out at 10 to the minus 10 is because that's the tolerance that we use to simulate this particular data set. So this turns out to be a controllable trend if we look at the box on the bottom right, discretizing the weak form with this test function, and the trapezoidal rule gives us an error of delta t to the p plus 1. So we have this sort of controllable accuracy in the case of zero noise. When we do have noise on the data, which is obviously the most common case, we found that there was a nice connection between this convolutional weak form and the parameters of the test function that was kind of fruitful. So what we found, if you consider the convolution is being computed using FFTs anyway, what that amounts to is multiplying the spectrum of the test function by the spectrum of the data set that you're given. And so we can look into the spectrum of the data set, find a point which demarks sort of the region where we have signal-dominated modes and the region where we have noise-dominated modes, and we can assign or design the test function to decay over those noise-dominated modes, and using some change point algorithm in this case. And the effect of that is on the bottom right, where we have a slice of a solution to the Kuramoto-Sivashinsky equation. And we're trying to approximate the weak fourth derivative, and it has 50% noise. And what we see using this sort of algorithm to select the test function is that the noisy fourth derivative and the clean fourth derivative are essentially lying on top of each other. So those are the some of the main pieces of the W-SINDI algorithm. There's also a particular brand of sparse regression that we use, and some rescaling and other things that go into the algorithm that I'd be happy to talk about afterwards, if anyone's interested. But the effect of the algorithm can be seen on a few test cases. One that we like to show is this Kuramoto-Sivashinsky example, in particular because it has a fourth derivative and a particular form of three terms we'd like to identify. If we're trying to approximate that fourth derivative using a noisy data set, we'd be hard-pressed to find a method that doesn't have high errors. But if we use the weak form to identify this model as I've described, what we see is this table here. And just to go over what we're looking at, the noise level that I've been talking about is the L2 norm of the noise divided by the L2 norm of the clean data, so that 100% noise in this case just means that the noise that we're adding to the data has the same L2 norm as the underlying solution. And then we measure the accuracy that we recovered the coefficients using this E infinity norm, which is just the relative infinity norm of the weights that we recovered. And then this TPR, which is the true positivity ratio, measures how correct the equation is that we recovered. And that's the ratio of the terms that we identified correctly to the terms we identified incorrectly plus the terms we identified correctly, so that if you, say, identify 2 out of 4 terms of a model, then this TPR would be 0.5. So with these metrics, what we see with this example, if we don't have any noise in the data set, then we recover the correct model and with an error in the weights of about 10 to the minus 7, so about 6 to 7 digits of accuracy, and that's simply reflecting the scheme that we use to generate the data. If we push the noise level up to 25%, then we still recover the correct equation in all trials. So this is averaged over 200 different random instantiations of noise. And in this case, the coefficient error is still less than 2%. We go up to 50% noise. An example of that is on the top right here. We can still identify the correct equation in all trials. And in this case, the coefficient error is a little higher at about 7%. But we can still continue pushing this with 100% noise and still identify the correct model in 96% of trials. Although at this rate, the error is getting a little bit too high to be useful in the forward simulation. Another canonical case of interest is the Invissid-Burgers equation with an actual weak solution. So now we can recover models using just weak solutions, whereas the previous version of the Cindy algorithm is restricted to classical solutions of PDEs. So what we did is generate a solution on the top left that forms a shock at time t equals 2, and the shock simply propagates this discontinuity for all time forward. We can look at different levels of noise on this system, and we see sort of surprisingly robust results in this case. Looking at 25% noise, which is an example of that, is on the top right. We're getting less than 1% errors in the coefficients, and we're still identifying the correct model. And at 100% noise, we identify the correct model in 99% of trials, and the coefficient error is still less than 3%. So this is kind of the trend that we saw across a whole host of different PDEs. We considered Invissid-Burgers, Karamado-Sivashinsky, Korteweg-de Vries, nonlinear Schrödinger equation, Navier-Stokes, Forest medium, Sine-Gordon, and reaction diffusion. These systems are differing in the number of dimensions they're over and the number of non-zero terms in the model. So starting with Invissid-Burgers with just one term in the model, all the way down to reaction diffusion with 14 terms. So a whole host of different equations. But the most important thing to realize here is the speed at which the algorithm runs. So to recover each of these models, the algorithm runs in under 2 minutes. And in particular, if we look at the Navier-Stokes dataset, this dataset is 233 megabytes, and the algorithm just takes 12 seconds to run. So if you were to watch the equivalent size high definition YouTube video, that would take about 4 minutes. And we're recovering the model and identifying the coefficients in a fraction of the time. So this really motivates considering using this weak form approach in an online setting where the iterations need to be performed very quickly, and overall computational efficiency is the main aim. So now let's look at this online extension of the W-Cindy algorithm, as well as just a light review of some online optimization facts before going into the algorithm. So what is online optimization? It's simply this problem in the box where we have an objective function ft that is dependent on some parameter w, as well as a possible data set ut, and we consider that this in particular function ft is changing over time, so that at each time we have a new optimal solution w star, and we want to write algorithms that approximate w star at each time t, given that we can only see a certain slice of the data ut, and in this case we're considering that we have a collection of snapshots, this kmem snapshots, that we can use to minimize this function ft and approximate w star. So what characterizes this kind of problem is, of course, the dynamic objective function, the limited memory. So we don't assume that we have unlimited, like kmem being an unlimited batch of snapshots. We assume that this is really sort of an order 1 quantity. And in particular, the small inter-arrival time. So this delta t characterizes the time between snapshots arriving, and the goal is to write an algorithm that approximates w star of t before the next snapshot comes in. So this severely limits the amount of time that we can take to minimize any of these objective functions ft. The other last piece of this, in the most interesting cases, the solution is actually required at every time t. So we're not looking for arriving at the t goes to infinity limit correctness of the solution. We actually want to approximate w star t at every time so that it can be fed to some controller, let's say, and made use of. So just for clarification, online optimization, online learning, time-varying optimization, these are all ways to describe this kind of problem, although they differ in the assumptions that are being made. But what we tried to consider is all of these 4 bullet points in one, that we have the time-varying objective, we have limited snapshots, small inter-arrival time, and that hopefully in some future application, we will actually use these solutions for some control. As far as theoretical results go, due to the small inter-arrival time, what's often considered is the few iteration case of existing algorithms. So if you consider minimizing a single ft at time t using gradient descent, in the online case, we'd be just taking one or several steps of gradient descent before the next solution, the next snapshot of data arrives, and we have to start fresh from the initial condition that is the previous step. So a popular online algorithm is the proximal gradient descent given in this box, where our objective function might be the sum of a smooth function g of t and a non-smooth function h of t. And we simply just take one step of proximal gradient descent from our given approximate solution w hat to arrive at the next approximate solution w hat of t plus delta t. The success of these algorithms is often measured in the terms of dynamic regret, where we're just taking the difference between the objective at our approximate solution and the objective at the true minimizer and summing up all of those differences over time. And what's often looked for is a sublinear regret, so a regret growing less than a constant times t. But a surprising result in examining many common algorithms is that simpler algorithms tend to outperform accelerated ones. So in the image on the top right, what we see, we're looking at conjugate gradient, Nesterov accelerated conjugate gradient, the heavy ball method and conjugate gradient, and the gradient descent, simple gradient descent, outperforms all of these methods on this moving least squares problem. And the heavy ball method, which performs much more accurately than gradient descent in the batch case, actually diverges over time. So this and other results are found in this review article by Professor Delaunay. And a canonical application of this kind of algorithm is this image segmentation problem. So what's happening in this image is that we're taking snapshots of traffic, and we'd like to decompose the image into a low-rank background of just the road and a sparse foreground of the cars. So let's say we can judge the traffic that's on the road. And since the traffic is moving, we don't have much time to estimate this decomposition. And but this is ongoing work to arrive at a better version of this. So in this 3B on the right, we're doing just 10 steps of proximal gradient descent before the next clip. And you can see all the way on the right that there's a pretty good separation between the cars and the road. Some other applications are for medical devices, sort of monitoring blood sugar, or wind turbines and other renewable energy regulation, and of course for self-driving cars, which might also fall into this online image classification problem. For our purposes, what we'd like to do in the online context is, given that we can only see a small snapshot of the data, identify the correct model and estimate parameters which might now be time dependent. So we're again considering this time-dependent objective function, and at each time we build a smaller linear system from k-mem snapshots of the data, And then our objective function is this time-varying L0 regularized least squares cost function that's in equation 6. So we tried a number of single-step methods, sort of, and arrived at the single-step proximal gradient descent method, where we're applying the proximal operator to the L0 norm directly to arrive at a hard thresholding operator, and we're just doing a single step of gradient descent and hard thresholding to arrive at the next solution. We also have this update in the threshold, which is sort of a decision tree update, and it's kind of a work in progress. But the pieces of or the restrictions that we'd like to consider are, again, this limitation in the number of snapshots that you can keep in memory, and that we only want to process the incoming snapshot at time t, and possibly integrate in time over the previous snapshots, but not have to operate on this whole script ut of kmem snapshots. And with this, we don't have to do any least squares solves to arrive at the weights. So going back to this nonlinear time-varying wave equation problem, what we see is that we do in fact identify the correct model over time and approximate the weights, but this sort of serves a purpose of that's more than just in the online context. We think that this kind of it leads to an extension of to problems that were not previously able to be solved in the batch case, namely with time varying coefficients. So in this case, we have a wave speed, again, like the title slide, that abruptly changes. And what you're watching is not just a playback of the video and the algorithm. This is actually the time that it takes the algorithm to run between each frames, which is about 0.033 seconds. And as we can see, after a sort of burn-in period, we sort of latch on to the solution and approximate the wave speed very accurately. So looking more in depth at a number of different runs. So we just took the same parameters and 100 different instantiations of noise. So that was a 10% noise case. What we see is that all of these different runs sort of clamp onto the correct solution in a very accurate way. So the blue here is the range of 100 different runs of this algorithm. And after a certain point, we're lining up pretty well with the true wave speed that's in black. So while this might be used in an online context where we're feeding the model that we've learned along with the parameters into some controller, this also allows us to approximate arbitrary functions of time that might sit as coefficients in the model, whereas previously, if we're using a sort of Cindy approach, all of those time-dependent coefficients would have to be approximated by some basis, which would be included in the library theta, and it would make the library just balloon. And so if we utilize this sort of online approach, we can tackle time-varying problems much more efficiently. Another area of interest for the online approach is big data. So this is maybe not big data in the sense of extremely high dimensions, but a 3D wave equation, 3 space dimensions and 1 time dimension, does amount to a data set that can't easily be handled by 1 CPU. And so if we try to identify this system with this kind of data in the online approach, we can also do this in a more lightweight fashion. And around 400 iterations, what we see on the left is we identify the system if we have sufficiently many snapshots, in this case, 17 snapshots, and then we lock onto the system and remain approximating the coefficients to pretty high accuracy. So this is around 10 to the minus 3 here. And each of these iterations takes about 1.3 seconds. So what we can glean from this is that the weak form approach can possibly be very well suited for online PDE discovery that might be useful for a variety of applications in control, especially because of the computational efficiency and the way that the weak form naturally handles noisy data. It also opens the door to time-dependent models, so being able to learn models that have either time-dependent coefficients or possibly time-dependent sparsity structure, which is something that we're looking to tackle in an extension of this. Um, and it might be a new paradigm for large data sets. So this 3D wave equation was just one example, but it's possible that looking at other larger PDE data sets in an iterative online way might be more favorable. Some things that we're looking at theoretically analyzing are the link between the success of the algorithm and the resolution of the dynamics. So it's not a clear relationship between the inter-arrival time delta t and the number of snapshots that you need to keep in memory, for instance. And then also this proximal gradient descent method that we're using with the L0 norm. It's also known as the iterative hard thresholding algorithm. And it actually is lacking in many theoretical results. It sort of was introduced around 2008, 2009, and then forgotten in favor of other sparse regression algorithms. But we think this might be a fruitful thing to reconsider and hopefully prove some sort of support recovery, given that empirically we see that. As far as extensions in the online case, what we noticed recently is that we've been using data sets with very high resolution. In fact, higher resolution than we might need. So in our original PDE weak Cindy paper, we reported results for the Navier-Stokes system with this data set, which is sort of hundreds of points in X and Y. But we found out recently that we don't actually need data sets at that high resolution. We can significantly downsample the resolution and still arrive at correct identification of the system with pretty high accuracy recovery of the weights. So in this case, when we took the large data set, we had a coefficient error of 3.7 times 10 to the minus 3. We go down to this super subsampled data set, the coefficient error is 6.6 times 10 to the minus 3. So not a huge increase. And hopefully we can use this sort of downsampled effect in the online setting as well. So ongoing work again is the wound healing problem, where we have successfully identified sort of the celebrated advection diffusion kind of model for this phenomenon, but it's not exactly adequate in that it's missing many of the features. So from there, we went down to extending WCindy to handle interacting particle systems and related mean field equations from those interacting particle systems. And this worked out rather well. With particle data, we can build sort of cheap histograms of the data, and the weak form can naturally deal with sort of pixelated, non-smooth histograms and allow us to recover interactions between cells and local potentials and so on using the mean field formulation of interacting particle systems. In this setting, we also were able to derive some theoretical results. Namely, we get the Monte Carlo 1 over square root n convergence in the number of particles as n goes to infinity. And on the opposite side of mean field limit of particles, if we just consider single cells and single cell models, another recent thing that we just released was a way of classifying cells and learning models for a heterogeneous population. And what we do, a key piece of that is to take this population of particles that you're given, or cells in this case. So this is actually experimental cell trajectories that you're looking at here. Learn individual models for each cell, and the blue curve is a playback of the learned model given the red curve, and use this ensemble of models to classify the given population into species based on modes of interaction between species. So in this figure here, we considered a simulation with 3 different cell types, each following different rules of interaction, and we're able to use this approach to both classify the population into the 3 species when they are initially unlabeled trajectories, and arrive at appropriate models for each population. So this is work that was just recently accepted at Journal of the Royal Society Interface. So these are the things that we're focused on now. Thank you very much for your time, and I'm happy to take any questions.